All right, guys, question 51. The probable fate of our sun. We talked about this. Our sun is not a huge star, so it will not blow up. Our star will slowly expand. It will turn into a red giant. Okay? It might flash a little bit, and then it'll eventually turn into those embers of a star, which we call a white dwarf. Okay? Our sun is not big enough to become a black hole. Our sun is not going to become a blue supergiant. Okay? And it cannot shrink and then expand. So that's why those choices don't make sense. Question 52 used to be on the reference table. They used to give you the wavelengths of visible light. They don't anymore. So you can just skip that one.
I still don't understand why that's not on there.
Question 53. The radiation that passes through the atmosphere and reaches the Earth's surface has the greatest intensity. Basically, what this is telling you, if you look at this, right, is that we get, most of the light that we get at the Earth's surface is what kind of light? It's visible light. It's not any of the other ones, because if it was, we'd all have a hell of a lot more cancer than we do today. UV radiation causes cancer. Gets blocked by what layer of the atmosphere? The ozone layer. Yay. Infrared radiation. While we do get some of it, most of the infrared radiation in our atmosphere is re-radiated from the land or the water or given off by creatures through metabolism and stuff like that. Okay? And radio wave radiation. We do get some of it, but a lot of these long wave waves do get bounced off by the upper ledges of the atmosphere.
That's also why you see rainbows.
54. Which type of surface absorbs the greatest amount of electromagnetic energy? We talked about this. What kind of shirts do you wear in the summertime so you don't get hot? Light. Because you want the light to bounce off. What kind of clothes do you wear in the winter so you do get hot? Dark. So you want dark colored. Okay, and we talked about how if you're smooth like a mirror, light hits it and bounces straight off. When it's bumpy and and has dents in it and is uneven and rough, it's going to get absorbed. So that's why it is rough and dark colored.
It's the difference between when we teach in the lab versus teaching in the classroom. In the lab, if you guys are all talking, we have to scream over you to get your attention. If you're talking in the classroom, we don't. Why? Because in the lab, everything is white or light gray and smooth. Whereas in the classroom, we don't have that. We have more, you have posters, you have cork, you have windows, you have all kinds of things.
The desks are more uneven and everything. Okay, on to the chemistry questions, Mrs. G.
Okay, so it's talking about which location will the density of air being the greatest. So come here, Mr. G. All right, so here we have our heat source, right? Remember, these are convection currents, guys, that come from the heat source. Doesn't matter if we're talking about air or if we're talking about liquid. Convection currents happen everywhere. So if this is our radiator right now, right? As the heat heats up the air, basically, the molecules are going to move further apart. When Mr. G explained it in the earlier video, as the molecules move further apart from each other, they get less dense, which is why hot air rises up. Well, if you get further away from the heat source, you're going to start to cool down. As you cool down, those molecules get closer together and fall or sink, right? When they fall or sink, that's where they are more dense. So E is going to be your answer because, again, as the heat heats up the molecules spread apart, become less dense, and rise up. When you get away from the heat source, they cool down, come closer together, and fall down. And this is where it's going to be most dense because those molecules are going to be on top of each other, okay? This question is your lab. We did this lab, right? Except we did land versus water instead of just sand. So it's asking you, most of the energy from the light sources were transferred to the sand by the process of. Well, it's going from the light. This is just, we basically imitated what the sunlight does, right? So it's basically the sunlight is going to be by the process of radiation. It's not conduction because conduction is when one thing touches another. It's not convection because we're not creating convection currents like we just saw. It's not transpiration because that's basically evaporation from plants, which is not happening here. It has to be radiation. Okay, 57 says, which phase change requires water to gain 2,260 joules per gram? Have I ever asked you to memorize it for this class? No. So where is that located? That's going to be located on reference table page 1, and specifically properties of water, because it says the word water. It also says to gain. To gain is also another way of saying to absorb. So it's talking about 2,260. So here, actually, you don't even have to know absorb because it says heat energy gained during vaporization. Vaporization is when you go from a liquid to a gas, which is way more than they're even giving you in these answers. Because if you look at it, it's not solid ice melting, which is a keyword in the reference table. That's out, right? It's not liquid water freezing, because again, that's out. Those are both 334 joules, either gained or released. For it's either going to be heat vaporized or condensing. Well, according to this, you're saying specifically to gain it, you need to gain energy for a liquid to go to a gas. How much do you need? 2,260. So that is your answer. Okay, this question, all right, you're given the heating curve, but do you even need the heating curve? Not really, because you're not changing the temperature. I mean, you're not changing the temperature, right? Because it's specifically saying how many joules were required to change 10 grams of liquid water at point D to water vapor at point E. So now, right, you're always writing out a given list, right? What are you given? You're given a mass of 10 grams, okay? And it says you're going from liquid water, so you're going from a liquid to a gas. So it doesn't really even matter. This graph does not matter anything. Why? This is what does matter. What we were just looking at on page 1 here is the fact that you were going from a liquid to a gas, right? So this is going to be a Q equals MHV question. Did you teach your kids this one?
Mm-hmm.
Okay. So here we have 10 grams, right? Heat of vaporization is going to be 2,260 joules per gram, right? And 10 times any number, you just add another 0, right? And that's going to be joules, because grams are going to cancel. And so it should be 22,000, right? 600.
And guys, the other way you could do this without doing the math is the chart on the reference table says how much energy it needs to raise 1 gram. So if 1 gram is 2,260, 10 grams is just that number times 10. So you didn't have to do that much math.
Okay. Earth's coldest climates near the North and South Pole are mainly because, compared to the rest of the Earth's surface, these regions, well, think about it. There are times during the year where the North Pole and the South Pole do not get any sunlight. They have 24 hours of darkness. Why? Because they're tilted away from the sun during that time, right? So they're going to receive less sunlight. All right, and finally, right, on September 23rd, the duration of insolation at all 4 locations is 12 hours. That should tell you right there that that's one of the equinoxes, because at the equinoxes, we receive exactly 12 hours of sunlight. So it doesn't matter if it's the spring or the fall, okay? The sun is going to be directly overhead at which latitude? Automatically, guys, E for equinox, E for
Equator.
Right?
Guys, there's not many dates that we ask you to remember in this class, but these 4 dates that are right here, March 21st, June 22nd, September 23rd, and December 22nd, 21st, are the few dates that we need you to remember. You need to remember when the equinoxes happen, and you need to remember when the solstices happen.